welcome you warmly to this first webinar in the ESCAPE project, where the OSSR work package will show you how our ideas are about enhancing science through sharing software. What are the benefits and best uses? So please, next slide. I'm going to show you a little bit of an introduction. So first, what's on our agenda? My name is Kai Graf, and I'm the coordinator of OSSR, and I will show you what we have done so far and what we are developing in OSSR. Next, Enrique from Lab CNRS, who is a data scientist there, will show us how the FAIR principles are set into the ESCAPE OSSR context. And Thomas of the same institute will show us how to encourage common software use developments within the CTRA S3. Next slide, please. Then Alex, who is regional center scientist at SKO, will show how he's providing workflows for the scientific reuse of SKA data. And last but not least, Elena will show us from EGO, will show us how to explore scientific data with innovative techniques. Then we will have a question and answer session where we all ask you to collect your answers and give them there orally, or simply put them please in the question and answer slot in this webinar, where you see a button at the bottom of your screen. So let me start with an introduction of ESCAPE. So ESCAPE is the cluster of the astronomy and particle physics S3, which link together the knowledge and know-how into the EOSC, the European Open Science Cloud. ESCAPE has is going to deliver a thematic cell of these clusters into the EOSC, and we have different work packages, and the work package we are concentrating today on is the ESCAPE OSSR, where we are clustering together our common efforts in software and derivative of software to make them available in a repository. Next slide, please. Our aim is really to have a shared open science product, and when I'm talking here about open science product, it's really the center on the software and derivatives of software, so workflows and services based on that software, and make them sharedly available based on the FAIR principles. So all of our objectives, and I know this is now a really high level, you will get examples of all of that during that webinar, is really that we want to facilitate and support the development, the deployment and exposure of the partner software and services. We want to foster the interoperability via software reuse, but also cross-fertilization between the S3s and of course also beyond this community, for example, in simulations. Also, we offer an open innovation environment where we generate open standards in workflows and data formats, but also common regulation and shared novel software for multimessenger and multi-probe data in our domain. All of that follows the paradigm of really enabling open science. So having in mind that all of that should be openly and be reusable by an as wide community as possible. It is, of course, a community-based approach, but it is completely inclusive. So all we are showing here as developments are now the starting developments within the community, but they will in the end be inclusive to all of the community and include also the onboarding of your software and services. Of course, it's based on the FAIR principles, but with a special focus, as I said, on the software part and also on the federation of available resources. So we know there are solutions out there, and we don't want to duplicate. We want to onboard as much as possible those solutions. Next slide, please. So two workshops we already have or have planned are already showing those co-developments and the community engagement. We had a workshop on open source software life cycles already last year, and we will have one in March on innovative workflows in astro and particle physics. So if you're interested, it's open for registration. Next slide, please. This is how our prototype currently looks like. So as I said, we want to onboard. So there's quite a lot of coordination, co-development between the EOS core, but also the established community platforms and solutions. And at the bottom right, the OSSR, where we have a landing page, a development platform, and a repository currently in a prototype stage. And we co-develop with our basis on the S3 on the bottom, and will enable that or put that onto the EOS catalog of services. Next slide, please. So this is, and you will get more information on how it's technically implemented in Enrique's part of the talk. This is our prototype. So for the development platform, we use currently a GitLab instance, but the possibility to use your own GitHub, GitLab, whatever you're using as development platform is possible. In the center, we have the landing page where the users come in. And at the right-hand side, we have the back repository where everything is stored and kept and aggregated. And that's a Zenodo community at the current. And with that, I hand over to Enrique. Thanks a lot.
Thanks a lot, Kay. Okay, so no need of presentation. If we go to the next slide, please. I will start. Yeah, I will basically speak about the fair approach that we have taken in the OSSR in the Escape repository. So I will start presenting a very nice example of an open science project that is the TrueCAD bundle. So basically in this project, the authors, rather than doing their own analysis and were taking out their own conclusions and everything, they have taken data that it was already available and open, and they have done a reanalysis. And rather than just keeping and making a publication, they have opened this analysis and study to the public. So if we go to the next slide, please. We see how this same project has been already published into Zenodo. Here you can see the interface basically of Zenodo, and we can see how this project fulfills basically all the FAIR principles, and that basically it fulfills within also using the platform that the repository Zenodo. So we have on one side the source and the data. We have also which is the license in which of the project. We have the way how to cite them and by whom it was cited, and also all the links to the different projects articles, and as same as the different metadata and or the schemas or formats that it can be exported. So if we go to the next slide, please. We can also see from their Git repository that they have provided a link to Binder, that it is no more than an online analysis platform where you can basically run again all the analysis that this project provide in the source code, and you can basically play around, take some data, and tune it and do your own analysis. They also provide a Docker to ensure reproducibility, and so basically a nice example of open science that fulfills basically the FAIR principles. So if we go to the next slide, please. How do we get here? The answer might seem straightforward, but basically by promoting and implementing the FAIR principles. I will not stop into them because I will just show how the OSSR are promoting them in a second. So if we go to the next slide, Basically, the second point of how to get here is by providing the infrastructure and services to host FAIR contributions. And I will not stop much because this is linked to case talk. So basically, on the OSSR prototype, we are providing already a Git repository connected with the Zenodo repository that is a general purpose repository. So if we go to the next slide, please, I will just show how we are promoting and approaching these FAIR principles within this OSSR prototype. So the first one says that metadata must be findable. So basically that it must be described by a rich metadata and use a unique way of find this entry, let's say entry or digital resource already. So basically already by creating an entry within Zenodo, you are already receiving a persistent DOI, so basically a digital object identifier, and you must provide a certain amount of metadata that well, it will basically be exportable and available within the platform. So if we go to the next slide, please. The next one, the next principle is the accessible one. Accessible one that basically says that metadata must be findable even when data is not longer available. So metadata must be findable if there is the case that data disappear for any reasons. So basically, Zenodo is a long-term archive that is already archiving the it is hosted by CERN and all the LHC and many others project data. And well, not to get into details, but they are using protocols. That is the Open Archive Initiative of Metadata Harvesting Protocol to basically find and harvest metadata. If we go to the next one, please. The third FAIR principle is the interoperability. So basically, metadata must use the applicable language of knowledge representation. That this means that it is basically to use a metadata schema. There are different metadata schemas. So for the moment in the OSSR prototype, we are using one of them. Zenodo accepts to export metadata in different schemas, and well, this will evolve for sure, but we are already in the OSSR prototype fulfilling this principle. Lastly, if we go to the next slide, the reusability, sorry. We are basically promoting it also by defining a clear license that and encouraging people to use an open one, of course, and also to providing enough information on provenance. At the same time, well, in this prototype, we are also automatizing the way of building images and providing them to the OSSR. So we have seen that, okay, if we go to the next slide, we have seen that this is the escape repository, so basically the OSSR, but this is, let's say, a mind map of how escape, all the services within escape will be connected, and basically without, I mean, this is just a mind map and quick schema, then we'll see that all of them will be possible basically if we promote these FAIR principles, because basically in the moment that we make things open, findable, accessible, and reusable, all the services like the development platform, the virtual observatory analysis platform, and everything will be basically automatically connected. And if I go to the last slide, please. So this is precisely where we are. So we are providing already within Escape and the OSSR prototype where the environment is already connected, and there's a big work in progress to connect with the rest of services. The same happens with the with the FAIR principle. So basically defining the basics within the OSSR has been already done, and there's a big work in progress to do this with the rest of escape services. So yes, thank you for the reminder. What we aim basically for Escape and for the OSSR, it is like, well, sorry, I mean, it was, so, okay, that's it. Thank you very much for the presentation.
Thanks, and we head over to Tuma.
Yeah, hi. So I'm the next one, Thomas, and I will tell you a bit about projects that are developed under ESCAPE in astroparticle physics. So next slide, please. So yeah, I want to give you a bit of an overview of projects that are developed under ESCAPE and that providing common developments. This is not an exhaustive view of what is developed under ESCAPE, but in 10 minutes, I have to show you a subset. Next slide, please. Yeah, we can directly go to the next one. So I will start with, next slide, please. Start with AGNPy. AGNPy is a tool, a Python tool, which is developed under ESCAPE using the whole AstroPy ecosystem, which is a big package used in astronomy in Python. And AGNPy aims to provide a core library to compute multi-wavelength photon spectra produced by leptonic radiative processes in AGNs, in active galactic nuclei. So with this library, you can really reproduce the models and the spectra that different modeling have been producing in the past. And you can build on top of these models. So this is really a package providing the core models to build more and more complex models, but in a very open way and reproducible and reusable fashion. Next slide, please. So this this package is part of the OSSR. It has been onboarded, and you can find the code, the source code in the OSSR at the Zenodo link. It is also fully documented and has, of course, an open license, which allows you to use it and use and modify it for your own purpose. You can see the full presentation at the link provided, and you can cite, of course, the package. Okay, next one, please. Then I'd like to talk about indexed.conf, which is a package developed mainly for deep learning to allow convolution and pooling operation, which are the core operation used in deep learning, but to be used on non-Euclidean grids of data, because all the frameworks that exist today work for very traditional images like with square grids. But in physics, in many experiments, we have very specific detectors. And this was, for example, the case for CTA, for the Chancroft Telescope Array, where the cameras don't have this traditional shape, and they have hexagonal pixels. So we developed a solution to apply convolution to this kind of images, but the solution is very generic and can be used to a large variety of problems, so to other physics experiments that are in the ESCAPE environment. Next slide, please. So the code also is completely open source and available in the OSSR. You can follow also the documentation. It's under a MIT license, which is completely open. And it comes with all also the examples, so you can rerun everything that is presented in the paper. Okay, next slide, please. Then I'd like to talk about Concordia. Concordia is a set of containers for Corsica simulation on Dirac. So as you may know, Corsica is a library used to produce Monte Carlo simulation of showers, of atmospheric showers, or even any type of shower. And this simulation can be very heavy and have a complex environment to build. So this package is providing containers ready to be used, and also providing a GUI that you can use to find the container that you want to have your specific simulation ready to go. So the use cases are several in ESCAPE already, with Game3net, CTA, and myography, and it will help many experiments. Next slide, please. So you can find the developments done under Escape on the GitLab platform. It should be released very soon in the OSSR with so in Zenodo, and you can see the full onboarding presentation under this link. Okay, next, please. The other example I wanted to show is glike, which is also a Python code, but based on root for the numerical maximization of joint likelihood functions with only one free parameter. So it can be used to really combine this likelihood. And the use cases are mainly also for glike. It can be used for dark matter, for signal events, for quantum gravity also. So many examples that we find in Escape in astroparticle physics. So next slide, please. You can find also the source code onboarded on the OSSR and on the Zenodo repository, all the dev and documentation on GitHub, and of course also it's under an open license, so you can reuse this library for your own. Okay, next for the last example, under Escape also are developed deep learning frameworks for CTA. So the purpose of these deep learning approaches are to solve this issue where you have the raw data coming from CTA, which is on the left, the small video, and you want to find the type of event, the energy, and the direction of the event that has produced this small video. And we want to apply deep learning to solve this issue, but to apply deep learning, you need to run many experiments that can be very complex and have a lot of configuration. And so these frameworks, they provide a way for the user to rerun experiments and to have a reusable and reproducible science. Next slide, please. So there are two main frameworks developed in Escape, the GammaLearn and CityLearn frameworks. That you can find them under GitLab and GitHub, also under open licenses. And yeah, as I said, they ensure the reproducible and reusable deep learning experiments for CTA, but also for the Cherenkov telescope experiments. And they are built also on a common approach with an integration in the full CTA workflow with common input data format and common output data format, so that we can have common metrics calculation to compare the results between all the different experiments and all the different pipelines. And you can find developments of this data format under this link. Okay, next slide, please. So this is what I wanted to show you today. Of course, this is not an exhaustive list, as I said, so many other contributions are on the way. So stay tuned. Thanks.
Thanks a lot, Thomas, for this overview from the CTA side and also how to commonly implement that. Let's head over to Alex and the input from the SKA side.
Hiya, thanks. Hi, everyone. My name is Alex. I'm a scientist at the SKA Observatory, and I'm going to talk to you about some of the data challenges that we're doing there that help promote some best practices in terms of software. Next slide, please. So one of our main themes of our work is preparing users for SKA data access. So when users are accessing data from Telescope, they will be getting their data products via regional centers in their part of the world. And they will do most of the processing and analysis at these centers. So that means they're bringing their code and their pipelines to the data in the cloud, so to speak, at these regional centers. And in this diagram, you can see the sort of schematic of how the data travels. So it comes from Telescope, where there's a central signal processor. It then some pre-processing happens at what's called the science data processor. And then the data products that are actually available for users are hosted in those pink boxes at the regional centers. So that's the part that users see. And we have been developing data challenges that are designed to represent the workflow of users interacting with data products to help promote some of the best practices in software and pipeline development that are going to be essential for this kind of work. Next slide, please. So yeah, so the data challenge is being aimed at motivating users to follow certain practices. So one of which is coding standards. So that means things like having an appropriate style guide, having documentation and comments, and using functions, classes, having modular code that has version control in it. And implementing those things when they're doing the data challenges, hopefully is going to help people have a better time. And then as well as publishing any results they get, it's becoming, well, it's essential that they publish their code and their workflow at the same time through tools, as others have said, Zenodo and GitHub become essential for this. So we're trying to promote that as well. And then all of that comes together in this ensuring that workflows are reproducible. So you need both those previous points, and then you also need to implement things like containers so that all software dependencies are taken care of and that someone can reproduce your workflow straight out of the box. Next slide, please. So this is a little diagram of sort of the reproducibility spectrum where you've got on the left-hand side publication only, so you only have results, and no one, well, users would have to go to a lot of effort to reproduce those results. And then at the other end, the gold standard, where someone can just grab a container that comes with the data that's all got versioned history and control, and they can fully replicate your results. And we want to try and push more people to the right side of that, that spectrum. Next slide, please. So Science Data Challenge 1 was run in 2019, and the challenge was to find sources in radio images like this one here. The images were very large, 32,000 pixels by 32,000, a couple of frequency bands. And when the challenge ran, a truth catalog was provided for a small area of sky, and the participants had to find sources and then report on how many they found, what class they were, and then they were scored appropriately. There was no requirement for participants to show their workflow or demonstrate it was reproducible. They just had to submit an answer. And that was a starting point. And we wanted to, and it was a good starting point. We wanted to build on that. So we, next slide, please. We developed a solution, a sort of model solution where people could use to see how they could improve. So in this, we developed a containerized example that does the whole workflow of finding sources and classifying them and reporting a score. And we developed that, and the code is on GitHub and GitLab, and the link is there, and the data is on Zenodo. And yeah, we were following all of the best practices that we wanted to promote in that workflow. Next slide, please. So in terms of what a user would do when if they wanted to rerun this, they would get Docker. So they would need some knowledge there. They would sort out their environment variables and aliases. They'd download the data. They'd create the Docker image, start the container, and then they would just run the script. And then in 3 hours' time, this whole pipeline would run. Next slide, please. So this pipeline does a couple things, just very quickly skim over it. It does some image pre-processing. So step one, you've got some prime beam correction, splits out sub-image. It has a potential to chop images up as well. It then does steps 2, which is source finding, and then step 3, model fitting, step 4, source finding on the whole image. Yeah, step 2 is just the training part of it. And then 5, predicting all of this, trying to find and predict the classes of all of the sources in the image, and then scoring the results. So this is a little schematic of all the steps that are happening, and all the parts of our code are separated up appropriately for that. Next slide, please. So that's been out for a little bit now. We're hoping that it helps share knowledge about technologies and techniques that can enable more reproducible results, and that people can use this for the future. And in the future, data challenges will test the reproducibility of results. So then containers become essential technologies for people who want to do analysis with SKA data. So Science Data Challenge 2 drew on this. So next slide, please. So in Science Data Challenge 2, the expectations were really ramped up here. And so this data challenge started in February this month, and it's running now, and it's going to run until July. So there are 40 teams doing this currently, 276 participants from all across the world, which is really awesome. And their goal is to find sources in this image cube, which is 1 terabyte of data in a single image cube. So in this workflow, users have been given access to resources. Several large computing facilities have joined in a challenge. So IRIS, INAF, there's a list there you can check out. And each of the teams is doing their processing at these resources. So they're creating their workflows and then bringing their code to the data, which is at these resources. They're not downloading the data. And when they are scored on how many sources they find, they will be tested on is their result reproducible. Next slide, please. And we came up with some criteria on those themes, whether the code is well documented, whether it's easy to install, easy to use, whether it has an open license, whether it's accessible code, whether the kind of coding standards it follows, and testing, things like unit tests. So we've broken down a lot of these categories, and we're hoping to, we've got some help from the Software Sustainability Institute, who are going to help score. They helped create this as well. They're going to help score the teams on just how well they've done here, which will hopefully also help promote and encourage people to try and do the best they can in terms of reproducing their results. Next slide, please. This is my final slide, just to conclude. So SKA Data Challenge 1 was a successful starting point. They had 9 teams competed, and after that finished, we developed an example solution from that. And then Science Data Challenge 2 is running now with significantly more teams, 40 teams, and that really stepped up the data size and workflow expectations. And we're really, we're excited about hopefully the teams really demonstrating some nice reproducible results and best practices with their software. And we hope these data challenges will help people prepare for interacting with SKA data, but it's also relevant for many other scientific fields where data volumes are growing rapidly, and these kind of technologies are becoming essential. So it's a great platform for spreading the word amongst other communities. And it's helping a lot with our prototyping and in terms of developing technologies for SKA regional centers. Yeah. That is all I had to say. So thanks very much for listening.
Thanks a lot, Alex, for this very nice overview of how SKA made good use of our common developments and set up best practices and spread the word around to reopen. With that, let's head over to Eleanor.
Hi all, I'm Elena. I work at European Gravitational Observatory and Scuola Normale Superiore in Pisa. Next slide. I wanted to introduce you to the innovative workflow that we are developing within ESCAPE. Why innovative workflow? Because as the previous speaker showed, in the next decades, we will face a period in which the big experiments will produce a very big amount of data, and we need to have a good solution to easy access to the data, to label this data, to approach the archives and find the source that we need, or to be able to be fast in classifying noise versus signal. For this, it will be even important that we will start developing a new paradigm for data analysis for these big experiments as SKA, CTA, Trinet, Einstein telescope, and Vera Rubin that will be operational in the next decades. Next slide. So the main point for this kind of new analysis will be for us even to do real-time analysis. So this will be important for the multi-messenger analysis that I will show in a minute. For us, it is important that we start working with open data, and this is something that you have seen is already ongoing. The big experiment start releasing open data, and we wanted to access to this data, to the software that we can use to analyze this data. We needed to be fast in the gravitational wave experiments to release alerts, because we are starting the multi-messenger analysis, astronomy, and so we have to be fast enough to send the alerts to the electromagnetic telescope to follow up any events that will be detected in the gravitational wave experiment. It is important that we start using a new data analysis pipeline that mostly are based on artificial intelligence and machine learning. As you see also in the other experiment, this already started. Next slide, please. What is machine learning? Is we hope that machine learn from our data and let us find what we want to find. So it is important that we can start with a good data sets. So we have to prepare our data set in a good shape, identify the right algorithm that we want to train, because it depends on the kind of data that we start working on, if they have been labeled by someone else or if not. And we'll try to train this pipeline. Even this could be a long phase of our pipeline, but once you trained your pipeline, you will be really fast in having a new prediction. So new data will come, and in few microseconds you can have prediction on the classification of the events that are in this data. Next slide. One of the most common approach that is used in machine learning is the deep learning, and especially the convolutional neural network. These are used for classifying in a good way the image. This is used in all the social network and all the daily life that we are used to. And we started to apply this algorithm also in analyzing scientific data. What we want to do is to start from a set of image, for example, where you have a certain kind of signal that could be a gravitational wave signal, a galaxy, a GRB, or whatever, a neutrino, and you want to transform this information in a probability of having the right classified events. And this can be done efficiently with this kind of network once you prepare it in a good way, also the image that you want to analyze. Next slide. As you see, this kind of pipeline have been already implemented in the ESCAPE partners, so for the neutrino search, for the solar telescope, for the CTA, and also for the SKA telescope. Next one. In gravitational waves, this is important because the gravitational wave experiment will be the first one to send out alert once we found some events that can emit even electromagnetic counterpart. The multi-messenger astronomy started almost 3 years ago in 2017 with the detection of the first coalescing of 2 binary neutron stars that emit also electromagnetic counterpart. We were fast enough to send out this alert and let also the other telescope to got information from this event. So this is important because we know that there are some kind of astrophysical source that can emit such a kind of information. And for some of them, we know which kind of events, and we know very well the theoretical waveforms of this kind of gravitational wave emission. For other of them, we don't know at all which kind of waveform we can expect. So we should be ready with this new innovative workflow to identify also this kind of source. Next slide, please. So this is something that we already started in gravitational wave communities. We start analyzing our data first with the simulated data sets. So we use the simulated data set, inject waveforms that we want to identify, apply this kind of machine learning pipeline to correctly classify the events. We started doing the same also on the open data that we release after a certain time of the ending of our scientific run. And this is important because we started releasing the data and also the software to access this kind of data and analyze the data through machine learning pipelines. Next one. One example of innovative workflow is this interaction that we had inside the working package 3 of Escape within 2 different communities, developing the machine learning workflow attached to a data versioning tool that is Hangar, that let us access to the data through a way similar to a GitLab approach. And we integrating this tool to our machine learning pipeline to detect and classify correctly the events emitted by core collapse supernova. This is something that is ongoing, and we are already prepared also the Docker to release this kind of software. Next slide. The big goal of our innovative group is to move to a real-time multi-messenger analysis. We know that such a kind of events can emit different messenger. What we want to do is to access to the data emitted by this, collected by the different experiment, approach the data through a machine learning pipeline to have in a fast way multi-messenger alerts, classification of the light curves, or gravitational wave source classification. With this in mind, we start developing a new framework in which we can analyze the data. Next slide. And one example is this Wayfire. This is a project starting within Escape program in which we want to create a framework where we can be able to access the data from the different experiment, attach a machine learning pipeline to the different messengers, and produce results that are accessible to the standard users. This is not an easy task, and that's why we need to move through innovative workflow, but also into a big cooperation within the group, because the data have a different way to be approached, to be integrated in this pipeline. So it is important to collaborate in this big vision. Next slide. So the next slides are a bit of a perspective. So what do we want to do? It is important to move to open data, open science, to be able to work with software that are produced in a different experiment, but that will be easy, accessible by each of us, in order that we can easily share and start this collaboration if we want to move to a real multi-messenger analysis that can be done hopefully also in real time. And that's all I want to say. Next slide. Thank you.
Thanks a lot, Elena. Thanks a lot for opening up this machine learning part, not only on the big data perspective, but also on the real-time perspective where fast responses are very necessary. And with that, we are through with our presentation. Thanks a lot for all the speakers being right in time. And it's time now for our attendees to ask questions, either in the question and answer, or also please raise your hands so that you can be unmuted and ask your questions. While we are waiting for the first question, we already have had one by Rudolf about the binary data formats that are used primarily also in machine learning and HDF5. So I already answered that quite a lot of the experiments are using HDF5, and as far as I know, also mainly the main Python-based workflows for machine learning are also using HDF5 as the standard formats. So following up in that regards would be very positive. So probably maybe Elena and Thomas, you want to answer in that as well?
Yeah, you replied, indeed, we use mainly HDF5. If we have other formats before, like the simulation data format that are very specific data formats, we transform the data and save it in HDF5 for the rest of the pipelines, which is much easier to use with many frameworks.
Exactly. I want to add that even in gravitational wave communities, we started with some format that is a proprietary format, but we are moving to HDF5 format because this is the common format, and it is easy to work with other experiments in this direction and to release data, even if, because we have to say that there are a lot of open software library that can make easy to read this kind of data.
Thanks. Seems there is no question at all. If we have no question at all by the attendees, here we have Susanna. Luigi, could you unmute Susanna or? No, please go ahead.
Okay, now. Okay, yes, I was wondering something that I don't know if this is the kind of question that you expect. I'm wondering in the first presentation that you have mentioned about the OSSR prototype, in which these two use cases are using Zenodo in order to publish not only the software but also the data in order to provide a DOI to this data, also to the software, etc. I was wondering that Zenodo has a limitation on the amount of data that you can upload to this catalog. So we are facing an era in which the data products produced by instruments like the SKA will be around terabytes. So just one data product can be 1 terabyte, and this is very difficult to store this data in one repository or copy this data in one repository. So we need to avoid to move the data, to copy the data in different places in order to publish or in order to facilitate the access to this data. So I was wondering if in the working package 3 you are working about this, or you have some solution or your thoughts about this.
Very good question, and it's a little beyond our work package, but let me answer to what we are facing here. So for the OSSR, we are really focusing on the software and services, and the data that we have presented here are really, as we have seen in the SKA use case, some kind of benchmarking data. So as you have seen also in SK, they will not, for data challenge 2, of course, provide the data challenge 2 data to Zenodo. Zenodo has a limitation, and we should not duplicate the data. But what we are planning for is to have a combined software repository where you have all the necessary data to actually run the code and test the code that is working. Or if you think about a data publication, a very high level data where the size is not really significant. For the lower data, there is the data lake project, which is also part of OSSR, where we and at the same time the science platform, where the analysis for that. So this is more the answer to your to your question about how to deal with really high level or low level data with large amounts. So there, the connection between the well-established centers of data and an overlaying analysis platform is done. And surely we will not copy all the data to our software repository. This is just linked in to analyze the data in the platform then at the end. I hope that is explaining that. And I'm pretty sure we will also have a webinar on our analysis platform and our data lake.
Good. Well, other comment is that we are also doing some similar work. So we try to make well, it's a study of which best practices we need to follow in order to support an end-to-end reproducibility. So I mean, from the very beginning of the data to the processing of the data, and then the plots that are in the article, in the paper. So we would like to reproduce all this process from the very beginning with the raw data that you need to reduce and process, and then produce the plots with the analysis information for the paper. And we also used repositories like Zenodo. In our case, we use UDAT in order to store our original data. And we find that we lack on metadata. So it's not this kind of environments that are very generic, like Zenodo or UDAT, they are not very specific with the metadata. So I think in the community, we prefer some services like, for example, the bio services that you can provide very specific metadata that allows you to make very specific search. So you can search by very specific properties, scientific properties of the data. But when you are storing this data in very generic catalogs, okay, you can put some kind of keywords in order to describe the data, but it's not so accurate like if you use services, community services, I mean. Yes. So this is one of the things that we found in our work.
That's exactly what we also found. As I said, we are more focusing on the software and the workflow description size, but also there we have, and Enrique can talk a little more about that. But on your provenance side, so the end-to-end reproducibility, as you said, also one of the work package of ESCAPE is the VO work package, where there's a strict data provenance schema, which we also try to follow and implement. So yes, this is, I think we can all agree to make data really fair, and if metadata is the key, and also for our case for the software and the workflow description. So which software to link together, which data can be used by this software, metadata is the key. But maybe Enrique wants to also say a few words what we did there.
Yes, so thanks, Kai. so, well, Susan, I think that you are speaking about very specific, really scientific metadata. So, well, basically what we are trying to solve for it is precisely a bit that, like from one side separate scientific metadata, and on the other software, or let's say software workflow data related metadata. Because this needs, I mean, if you want to find basically something, you need to, I mean, you usually go either through the through a project or through a repository rather than going directly to very specific cases. But yes, I mean, well, basically we are investigating the different schemas and different ways of solving all of these issues.
Okay. Thanks.
Thanks a lot, Susanna, for the question. And actually, I just got also the notice that it's time to wrap up. It's nicely because I see no further question. So if you have also further question, please don't hesitate. You have our contact in the webpage of the seminar. So I hope we were able to show you in this webinar our common approaches to co-development and exposition of software and services in the OSSR. What we will do next from our side is to finalize implementation, continue the software and service onboarding from our partners, but also the user communities, and then the full integration into the EOS. And we are, of course, always happy for cross-fertilization also across the communities. With that, I want to thank you all for being with us in this first webinar, and hope to see you soon again in the EOS community in general. Thanks a lot to all the panelists, to all the attendees, and also to our technical support by Trust IT Services from Luigi and Rita in the background that you usually don't see.
Thank you.
Thank you.
Thanks a lot, and have a nice afternoon.
Bye, everyone.
Bye-bye.
Bye.
Bye.
Bye-bye.